All right, everyone, we are back and we are about to solve our Pset 7 solutions. So let's go ahead and solve this problem set. So we have some very familiar systems, just like we looked at previously. Will this material fail via Rankine, Tresca, or von Mises criteria? The material is the black curve. So in this black curve, you really see, I can argue either you're going to say this is the linear region, so it's like 60 megapascals, or you can kind of even say this. I'm just going to say yield strength here is 60 megapascals. It's not quite well defined, but we need some more points. But let's just say that I would accept 15, or like the 17, 18 number as well. So let's go ahead and let's solve out. So to solve this problem, we need to remember how we solve the problem in our problem set. So you can actually just look those up. I'm just going to do this quickly because it's always good practice. Again, metallic material. Ooh, looks like there's an error there somewhere. Yikes. So there's probably a little error in a solution in an old video. Please don't put it, hold it against me too much. So 100 gigapascals, nu 0.3 for metallic material. We do have a thermal expansion coefficient. It is 3.2 times 10 to the minus 7. And we say that room temperature decreases from room temp. So the delta T is the final, so it's 15 minus 25. So the material is expanding, but we're pulling out. The L naught is 75 times 10 to the minus 3. We have our, our force in the 2,2 is equal to positive 15 times 10 to the 6. So our sig 2,2 is going to be equal to F22 divided by L naught squared. So we're pulling out. There will be a strain in the 2,2. And when we pull out there will be a strain in the 1,1. So there will be no strain. Sig 1 is 0. Sig 3 is 0. Because it's so massive compared to the rest. All right. So with that, we can actually, for this problem, if we're just looking at stresses, we can just now look at what is sig 2,2. Because that's the only stress that we have in here. So if we're looking at our von Mises, we're saying sig y is equal to 60 times 10 to the 6. So if we're looking at Rankine, we're basically saying is sig 2,2 greater than sig y? Yes, so that means it's going to yield. Is sig 2,2 minus 0, which is the other stresses. So basically, because again, in this problem, my sig 1 is equal to sig 2,2. My sig 2 is equal to 0. Sig 2 is equal to 0, which is equal to sig 3, which is also equal to 0. So is this greater than, so is sig 1 minus sig 3, just to kind of keep it in perspective. So is sig 1 greater than sig y? Is sig 1 minus sig 3 greater than sig y? True. And then finally, square root of 1/2. Square root of 1/2 times 1/2 times, let's do sig 1 minus sig 2 squared plus sig 2 minus sig 3 squared plus sig 3 minus sig 1 squared. So again, that's my Tresca. This is my von Mises. This is greater than sig y. Yes, it is. So they will all yield. So it'll fail. Basically, it's going to fail under every criteria. What is the critical crack size required to fracture, given that this material exhibits a surface tension and a fracture toughness of this? Can't use surface tension because we're looking at a metallic material. We can use fracture toughness, so we're going to use K1C is equal to F stress square root of pi a. So we know the stress is going to be the stress sigma 1, the 2,2. So let's go ahead and solve that. So let's solve that 150 times 10 to the 6 set equal to sig1 times square root of pi a. I'm just skipping that, geometric factor. And that would be my critical crack size. So it's actually quite large. Considering the stress that we're applying here, it's quite large to fracture. So I need basically something like on the order of a millimeter. What energy contribution pushes the material to fracture? So to fracture, it wants to relieve elastic strain energy in my bonds. To remain intact, I don't want to pay that penalty in creating surface area. All right, working with a polymeric material pipe, 2 strain gauges, et cetera, et cetera, et cetera. So again, let's figure out, we could even pull up our previous video, but again, it's fun to do things. I wonder if I have that here. I have the old, actually, yeah, I have it right here. So I'm gonna cheat a little bit. So this was our solution from last time. So if I have my sig h, so I'm just gonna say sig h equals this. So this would be the stress that I'm looking at primarily. Again, for fracture, because I'm looking at the largest stress. Initial crack size of this, will the material fracture? So I have fracture toughness and I have strain energy release rate. I can use either one because this is a polymer. So I'm just going to use the fracture toughness again. So I want to solve, will this material fracture? So I'm going to look at 78 times 10 to the 6 times 10 to the 6. Set this equal to, I'm going to do sig h times square root of pi times a. And if I have a crack size, so this is the critical crack size required to fracture. So if I have 100 micrometers, I'm good to go. It's fine. Now, on the other hand, let's go ahead and look at if we were to solve this with because the Griffith criteria is basically our stress at fracture equals square root of G sub C, our strain energy release rate over pi a. I believe that's the case. We could just quickly look at our, let's look at our chapter 6. Just want to make sure. My memory's pretty good, but it's always nice to have some to double check. Yep, I still got it. So here our stress at fracture would have to be, again, because we're looking at sig h, equals square root of basically 1 times 10 to the 9th times 185, all that divided by pi times a. So here, on the other hand, again, if this were the case, if we're using this criteria, then it will fracture. But again, both of those are valid, so we're good to go. All right, let's look at the deformation mechanism map. Fill out the regions. So this is our theoretical shear. This is dislocation glide. This is elastic. This is power law creep. This is going to be Navarro-Herring creep. And this is going to be Koval creep. The deformation map is created from the black material in the stress strain curve. Draw the deformation mechanism as the purple and the red curve. So purple and red, now we're comparing. Purple, red. One thing we notice is that these are definitely 3 different types of materials. Why? My Young's modulus are different. So when we're thinking of we can do basically work hardening, which is going to change the number of, basically our yield strength scales with the dislocation to the 1/2 power. We can look at basically solute strengthening, where the yield strength scales as the concentration of solute to the 1/2 power. We can grain size strengthen, which yield strength scales with just the grain size to the -1, and we can precipitant harden. These two, 1 and 3, are interrelated, so if I do one of these operations, I do the other. Typically, if I'm taking a material and I'm producing different stress strain curves using method 1 and method 3, the yields, my Young's modulus must be the same. So I know in this particular problem, from what we talked about in class, is probably 2 and 4 that are occurring. And that's not really going to change anything except for if I'm looking at my purple curve, my yield strength is lower than this black curve. So this line will decrease here. For my purple and for my red, it'll increase. It'll get closer to that theoretical yield stress. There may be some slight changes. Maybe the cobalt creep region increases a little bit for the red, because if you're solute strengthening, you can kind of change the grain size a little bit because of the addition of solute, but there's not going to be huge changes. If we were work hardening or grain size strengthening, you'd see huge changes in the cobalt creep region in addition to that movement of that line. Excellent. Possible strengthening mechanisms, we just talked about that. Scaling, got it. See, we did this problem before. Solved it before we even looked at it. If we were to work harden the purple curve, 10% and 90%, answer the following questions. Draw the stress strains for the purple curve. So I'm going to, so this is my, I'm just going to do it generically. So this is my purple curve. So this is purple. If I do 10%, it's going to have the same slope, higher yield strength, and typically it's going to basically die out sooner, 10%. And then 90%, again, same thing here, but die out even quicker. So higher yield strength, lower ductility typically. So that'd be my 90%. Boom, boom. The deformation mechanism maps, again, so now if we're looking at the work hardened, that's 90%. When we work harden, we basically increase the number of dislocations and we decrease the grain size. So what we'd expect is in that 90%, and in the 10% as well, you'd see a huge region here for cobalt creep. So it would grow. The 10% would just grow maybe slightly here, if this was indeed the purple curve. And again, you'd get the shift. Both of those lines, this would be my 90, and my 10% would be like a little bit above here, like that. Excellent. I expect you a lot larger, much more explanations, much more drawings, of course. This is just our quick solution video. What's strengthening occurring? And we've already done that one. So it has to be work hardening and it has to be grain size strengthening, because those are going to change each other. Let's look at the blue curve. Then we're going to precipitate strengthen the materials with a lower volume fraction, a higher volume fraction. So now, again, stress strain. If this is my blue curve, looks something like this. Now if I do lower volume fraction of precipitate strengthen, so lower volume fraction, it's going to look like this. It's going to be typically probably a slightly, just maybe slightly different slope, and then lower yield strength, and then it may have a little bit more ductility. Higher precipitate strengthening can have a slightly higher Young's modulus, and then higher yield strength for sure, and then a drop down, a little bit, a loss in ductility. Deformation mechanism maps, same concept goes as kind of the first problem. So we would see these two different, again, lower volume fraction, higher volume fraction for our, basically this line, which measures our yield strength at all temperatures. But you wouldn't see that change in the cobalt creep region because, again, in precipitant strengthening, again, you're not changing essentially, that cobalt creep region is governed by changing essentially the size of your grains predominantly, and we're not changing that there significantly. There are going to be slight changes, but anyways. Draw the curves. Draw the curves for the change in yield strength versus the three materials. Excellent. So if we look at the change in the yield stress versus precipitate radius, for the normal one, we'll just go like this. Lower volume fraction. Remember, we want to cut small particles. So we want to cut here, and we want to bow around larger particles because we don't want that surface area here. And the change in curvature is smaller for larger particles. So if this is our normal blue curve, if we decrease the volume fraction, it means that we're going to have a lower change there. We can cut. We're going to be able, if there's less, right, precipitates, we can cut more because there's not that huge change in that energy penalty. If we have larger amounts of precipitates, we're going to have a higher yield strength, and we're not going to be able to cut as much because there's so many of these particles in here. So it's going to shift the curve inherently to the left if we increase the volume fraction. What size particle will we cut versus bow? We just talked about that. So again, surface area and then curvature went over our principal radii here. That's it. So that is your problem set. So we'll do the last one in the next video, and we'll see you then. Thanks. Bye.